Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussions related to this particular course, Introduction to Electronics. We've been discussing transistors and amplifiers. So let's look at a very interesting and very popular kind of an amplifier and circuits built using that particular amplifier called operational amplifier, or in short, op-amp. Okay, so we've seen with a little bit of background that the design of these amplifier circuit is non-trivial. And even the simple amplifier circuit, we have to make sure that the transistor is biased properly in the saturation region. We have to choose R1, R2, RS and RD properly. And we have to choose the supply voltage properly. And also we have to make sure that for the frequency of interest, the capacitors act like reasonable low impedance paths. And therefore, it requires specialized knowledge to design a very simple amplifier like this. And often the amplifiers, this is what we call as a single stage amplifier consisting of one single transistor only. Often the demands of the application are such that we have to add several stages of amplifiers. And as an example, this shows a more practical circuit, MOS-based amplifier, and we can see that there are several transistors that are there, and there are at least two stages here of the amplification, and then the design becomes even more complicated. And so the point is that design of amplifiers requires a person with significant experience in analog circuits. And therefore, it's not possible for every user, every person who's interested in, let's say, in amplifying an electrical signal, to design his or her own amplifier. Even though MOSFETs are easily available, resistors are available, but the design is not straightforward. And therefore, the point is that a person may be an electrical engineer, may not be an electrical engineer, may be working, maybe a mechanical engineer or a civil, but may be handling electrical signals and may want to amplify a particular electrical signal, and therefore wants an amplifier. But then it's not possible or is difficult to learn how to design your own amplifier. So the point is then, if let's say there's a lot of demand for amplifiers from various kind of applications, then the question is, why don't we have experts, analog design experts, who design and implement amplifiers and make it available to everybody else? Now, so that's, yes, it's possible, but the difficulty with this is that different applications, different people will have different requirements. And therefore, if you think about one single amplifier which meets everybody's demand, so that particular amplifier is not possible. Either it will become too expensive, which can meet all possible demands, and in general you will not be able to design an amplifier which will meet all the specifications for all the applications. And the other thing is, so that is not possible. Then the other point is that we can't have experts design amplifiers for each particular application, because the demand from that application may be very less, and the analog circuit design process is expensive. The salaries of analog circuit designers have to be paid, and then the design has to be fabricated. So all that is a costly process. So you cannot have, if somebody wants, let's say, 100 amplifiers, well, you cannot get a company to design a amplifier, 100 amplifiers, and for that particular company. It's not, the design and fabrication is too expensive, and the costs are justified only when the volumes are high. So we are left with what this is trying to illustrate is that there are two ways in which design can be done. One is a design which is a general purpose standard design, and so you can go and pick it up from the market and use it for your application. Now it's a general purpose standard design, and therefore that particular design may have a fixed gain of, let's say, 100 or 200, fixed kind of input resistance, frequency response, and things like that. If it fits your application, fine, but many times it may not fit your application. So these standard amplifiers can be produced in large volume, but very often you may find that it's not built to the specifications that you desire. So that's a standard design, a design which is not catering to any one specific application, but to keeping wide variety of applications in mind. So somebody produces a amplifier and fabricates it and sells it. So that's a standard design. The other one is a design which is done specific to a particular application. So that's a custom design. Now, custom design is, as we said, is expensive and is justified only if the volumes are high. And if we said, if you require 100 amplifiers, well, asking somebody to do a custom design for you will be very, very expensive. So in between custom and a standard design, we have what is called as a semi-custom design. So the idea of semi-custom design is that it's a partially completed design. It's a partially completed design, and then the user adds a few elements to that partially completed design and customizes it according to his or her own application. So that seems like a compromise between these two approaches. Standard design is a fixed design. If you like it, use it. If you don't, well, then life is hard. On the other hand, custom design, well, it can be designed specific to your application, so it will be highly optimized, and but the whole process is time consuming, it's expensive. And in between is a semi-custom design, a partially completed design, and then you add a few elements to it, and then you customize it. All right, so that's a good compromise. And the other way you can look upon it is as semi-custom design is a design which you can program it. Now, normally we think of program in terms of software, but here you can program the design in the sense that you can add a few hardware elements and thereby customize it to your application. So op-amp is a very good example of a semi-custom design here. So let's start with the background that we need for understanding op-amps. So op-amps are made out of difference amplifier. So what is a difference amplifier? Well, as its name indicates, there are various kinds of difference amplifiers. We'll consider a case where the difference amplifier has two inputs, V-in1 and V-in2, and one output, V0 here. And so the difference amplifier is sensitive to the difference in the input voltage and insensitive to what is common between them. Okay, so let's define this mathematically. The difference in the input voltage obviously is V-in1 minus V-in2. So that's the difference voltage here. We call it VID, V input, D refers to difference. And what is common between them, we can define it as V-in1 plus V-in2 divided by 2, the average of the two. So C refers to the common mode input signal, and this is the differential input signal here. And the output voltage is now, instead of writing V0 is, note that it's an amplifier, so V0 will be equal to some constant multiplied by V-in1 plus some constant multiplied by V-in2. Instead of writing it like that, we can write it in this form. V0 is the differential gain multiplied by differential input voltage plus common mode gain multiplied by common mode input voltage here. So differential mode gain and common mode gain. So a difference amplifier is one where the differential mode gain is much, much larger than common mode gain. And in an ideal difference amplifier, the common mode gain will be 0. And V0 will be only equal to AD times VID here. And the ratio of the two, AD by ACM, the ratio of differential gain and common mode gain, is what is called as common mode rejection ratio. So an ideal difference amplifier will have ACM going towards 0 or CMRR equal to infinity. Okay, so let's illustrate that with an example. Suppose there's a difference amplifier with a differential gain of 100 and common mode gain of 0.01. So CMRR will be 100 divided by 0.01, so will be 10 to the power 4. And let's say VI1 is 1 volt 5 millivolts sin omega t, VI2 is 1 volt minus 5 millivolts sin omega t. So note that the difference mode signal here, VID, the difference of the two, is the sinusoidal signal here, 10 millivolts sin omega t. And the common mode signal here is the average of the two, 1 volt. So note that the common mode signal is pretty large, 1 volt, as compared to the differential mode signal, which is only 10 millivolt. But what will be the output? Output will be AD times VID plus ACM times VIC here. So this signal, this amplifier rejects the common mode signal here. So note that common mode gain is 0.01 multiplied by 1. So this gives 10 millivolt. Differential mode gain is 100 multiplied by 10 millivolt here, gives us 1 volt here. So what has happened is that the differential signal has gotten amplified, the sinusoidal signal has gotten amplified, and the common mode signal has gotten rejected. Common mode signal was 1 volt, it has become 10 millivolt here. So that's the idea behind a difference amplifier, that whatever is common is rejected and whatever is different is amplified. So operational amplifier is a special kind of difference amplifier. And what is special about it is that it has a very high differential mode gain. And it has a very high common mode rejection ratio. It has very high input resistance. So when you see from here, the resistance looking into this particular circuit is very high input resistance, very low output resistance here. And it has several other properties which we will not go into. So very high differential gain, very high common mode rejection ratio, or very low common mode gain, very high input resistance, very low output resistance here. And so in this particular course, we'll deal mostly with ideal operational amplifier. So this ideal operational amplifier, what happens is that differential mode gain will take it as infinite, very high. Common mode rejection ratio also infinite, which means common mode gain is 0. Infinite input resistance, which means that no current would flow into the op amp here, inside the op amp, because the resistance is infinite. 0 output resistance. And all other properties are also in an ideal sense here. Okay. Now, if you're wondering, do we have amplifiers like this? Well, obviously, these properties are not infinite, but they can be very large. So for all practical purposes, under the conditions in which we are using the circuit, the assumption of infinite differential gain or 0 common mode gain seem reasonable. For example, this is a very common operational amplifier that you would also use in the lab, 741. And if you look at the gain of the amplifier, well, let's look at this gain of the amplifier. It is 200 volt by millivolt here. So the ratio is 200 times 10 to the power 3. So the gain of this amplifier is 2 times 10 to the power 5. And common mode rejection ratio written in terms of dBs is 90 dB, typical value. So that's also 90 dB, 100 dB is like, again, 10 to the power 5. So these are very, very high values. Input resistance is high, about 2 mega ohm, but not that high. 2 mega ohms is, but you know, if your resistances in the circuits are of the order of a few kilo ohms, then input resistance compared to that is very high. So inside the op amp, there's a fairly complicated circuit. This is a bipolar op amp. And this is a bipolar op amp, and it's a fairly complicated circuit, and it should be obvious that designing such an amplifier will be pretty hard, and only experts with substantial experience would be able to design an amplifier like this here. And so that's why we are talking about a semi-custom design. So so this is, as you would see, this is not a complete amplifier, but you have to add a few more elements to make an amplifier of your interest. So the simple equivalent circuit of our op amp is the following. When you look at it from the input side, the op amp between these two terminals, this is called the non-inverting terminal, and this is called the inverting terminal. You'll see why these notions here, minus and plus. And so between V1 and V2, there is a resistance Ri. And in an ideal case, input resistance, in an ideal case, Ri is infinity. And from the output side, the op amp V0 is sensitive to V1 and V2. So the op amp is V0 equal to, is represented by this voltage dependent voltage source, A0L times Vi. Vi is, note that the difference between two, V1 minus V2. So it's a difference amplifier. So we are taking it as an ideal difference amplifier. So the output voltage depends only on the difference of the two, V1 minus V2, which is represented as Vi. And A0L is what we could call as the open loop gain. OL refers to open loop gain of the amplifier. And R0 is the output resistance of this particular op amp here. And so we just saw A0L could be as high as 10 to the power 5. R0 could be as low as 10 ohms. Ri could be a 1 mega ohm. And so if as we said, if the resistance in my circuit are, let's say 1 kilo ohm or so, well, 10 to the power 6 would appear as very, very high compared to that. Similarly, resistance is a 1 kilo ohm, something 10 ohms in series with it will also appear to be very, very low. And all right, so let's look at this particular amplifier here. So V0 will be equal to A0L times Vi here. No, so graphically this is how it appears here. If we plot V0 versus Vi, so it would go like this here. But then this relationship cannot continue forever. Cannot continue forever because there's a limit imposed on how high the voltages, output voltage in the circuit can be, depending on the supply voltage. So if we take a supply voltage, many times we will not show an op amp with a explicit supply voltage. It's understood that there's a supply voltage. And many of these op amps have two supply voltages, one plus VCC and another minus VCC here. So an example, this could be plus 12 volt and this could be minus 12 volt. So these supply voltages impose a limit on how large or how low V0 can be. So as you increase Vi, eventually what will happen is that the output will saturate. It cannot go beyond the supply voltage here on the positive side. Similarly on the negative side, and often you cannot even reach the VCC value here. You'll reach very close to it. VCC is 12. You may reach maybe 11, 11.5, maybe 11.7, somewhere close to it, okay? And similarly on the negative side, it will saturate again, just a little bit under minus VCC here. So the gain is very high, and so you have a really linear relationship, but the op amp gets saturated once you reach the voltage close to VCC and minus VCC here. Okay, so how do we use this particular op amp here? So suppose the op amp that we are given, we attach a voltage here. We attach a voltage and we would like to amplify, right? So if we apply a positive voltage here, note that if we apply a positive voltage here and this is ground, so V2 is ground, V1 is positive, output voltage will be positive. On the other hand, that's why we call it positive, non-inverting terminal. On the other hand, if I attach a voltage here to this node here and connect it, this part is ground. So this is positive. So note that V1 minus V2 will become negative and the output voltage will also become negative here. Okay, so that's why this is called the inverting terminal. All right, so how do we amplify? Suppose we have a 1 millivolt sine omega t and we are given an op amp like this here. So how do we amplify this particular signal? So let's connect this particular signal directly here. We want to amplify, so let's connect this signal to the non-inverting terminal. Inverting terminal, let's put it to ground and let's take the output here. So what would happen? Note that this amplifier has very high gain and very high input resistance and very low output resistance here. All right, so this is how an op amp looks like here. And let's connect it up. Let's apply Vs to the input here. V2 is ground. So that's what we do, A0L, Vi, V0. All right, so V0 will be equal to AOL, open loop gain, multiplied by Vi. And Vi is, according to a circuit, is nothing but equal to Vs. So equal to Vs, so V0 will become A0L is 10 to the power 5 and multiplied by 1 millivolt. So that becomes 10 to the power 2 sine omega t. But we said op amp is limited to plus minus 12 volt here. So this is saying that this will go to 100 volt sine omega t, but 100 volt is not possible because although not shown, there's a supply voltage of plus 12 and supply voltage of minus 12. So it cannot go beyond 12 and plus 12 and minus 12. So what will happen is the following. If we give a sinusoid like this, 1 millivolt sinusoid here, very quickly what happens is the output goes here and saturates. The op amp output saturates to about 12 volt here. And similarly on the negative side, it saturates here, minus 12 here. And note that how much voltage do we require? So this is 1 millivolt. And if I have something like 0.1 millivolt, 0.1 millivolt will give us maybe around 10 or so. So very quickly it saturates. And therefore, our amplifier is not working properly here. This is saturated here, this is saturated here. So one of the conditions for amplifier to work properly is that the output should look like the input here. And the output doesn't look like, it's totally distorted. So because the gain of this amplifier is so high, 10 to the power 5, if I want to amplify a signal, let's say even 1 millivolt, sometimes I may have a signal which is 10 millivolt, I cannot directly connect that particular signal here and get the output that we want here, because the op-amp will very quickly saturate. And so that's the reason why we said in the beginning that this amplifier is a partially complete amplifier. You have to add further things in order to use it. You can't simply connect an input and take the output and things would be fine. So that doesn't happen. So how do we amplify a signal like this here? Well, so 1 millivolt signal, we cannot directly connect to it in this particular manner here. So somebody may think, well, why don't we attenuate this particular signal to 0.1 millivolt and then amplify? So, but that's not a good strategy. To attenuate something, I mean, you want to amplify a signal and then you're first attenuating and then amplifying it again. And although we have not discussed in the course, every time you attenuate using a voltage divider and things like that, you add noise. Resistors are noisy elements, and all elements, all electrical elements, they add noise. And so it's not a good strategy to attenuate and then amplify. So what we do is the following. We make a circuit of this particular kind here, right? So there's an R1 and there's an R2. So that's what we said. We wanted an amplifier, but we could not directly connect the input and make an amplifier like this. But now we can take an op-amp, add two elements here, R2 and R1, and now this whole thing acts like an amplifier. Okay, so we have customized this particular one as an amplifier. Now you connect the source here and you take the output here. And we will show to you that V0 by Vs is simply equal to minus R2 by R1. And so if somebody wants a gain of 10, the application demands a gain of 10. So all you can do is you can connect R1 equal to 1K, put R2 equal to 10K, and you have a gain of 10. And it's very easy for anybody to design this amplifier. Somebody wants a gain of 20. Well, you put here 20K and you put here 1K and you get a gain of 20. Somebody wants a gain of 5. Well, you can get any gain that you want by simply choosing this ratio appropriately. So the design of an amplifier becomes so simple. Anybody, even a person, a school-going student, can design an amplifier using this particular approach, because all the hard work of designing has all been done by experts into designing this particular op-amp. And once you design this op-amp, now you can use it to build any kind of an amplifier that you want in a very, very simple manner here. Now, let's see how this relationship comes about. And further, note that our amplifier has feedback in it. So normally the amplifiers that we have seen, we have a signal and the signal propagates to the output like this here. As you can see here, there's a path to the output, right? So the signal Vs goes to this particular input here, and there's a path here, and there's a path through the op-amp, and it goes to the output. But we also see that there's a output is also being fed back to the input. A part of the output goes from here and is fed back to the input here. And this is what we mean by feedback. So most of the time the op-amps are used in a feedback mode here. And the previous case was the op-amp was being used in a open loop mode here. There is no feedback path here from the output to the input. So it's called the open loop mode here. And in this case, what we have is a feedback path. We say the amplifier is being used in a closed loop phase here. If the feedback signal helps the input voltage, we have positive feedback, otherwise negative. Okay, so let's look at this in a little bit more detail here. So let's look at the concept of feedback. So suppose we have an amplifier. So we apply an input and we get an output. So it's a normal amplifier, and we call it an amplifier in open loop condition. There's no loop where the output is being fed back. So no loop is being formed. It's like open here. But now, suppose we take the output here, we tap the output voltage here, and there is some network here, some piece of circuit here, which takes the output and generates a voltage which is proportional to the output here, and we feed it back on the input side here, right? So this is what we mean by feedback path here. So the actual input to the amplifier that goes here is not just the input that I apply, but it also has some part of the output being fed back to the input here. Okay, so that's what we mean by there's a feedback path here, and such amplifiers are called feedback amplifiers. Now we can feed it back the voltage such that if this is, let's say, positive, the voltage that I get from here, I can subtract it from here, so that the net voltage that I get is V in minus V feedback. So we call this as a negative feedback here. We call it as a negative feedback here because we are subtracting from it here, and you'll see why the negative feedback in a minute. On the other hand, we could also take it here such that we can add them up. So the feedback, the voltage which is fed back, is in sync with it or in phase with V in, and so it adds to it, and we call it a positive feedback here. All right, so a little bit more on this terminology here. So why is it positive? So note that suppose I increase this voltage here. If I increase this voltage here, and the gain is positive, A is positive, so this voltage increases. And the meaning of beta is that output voltage V0 goes as input here, gets multiplied by beta and appears over here. So, and beta is positive. So if I increase this, this voltage increases, this voltage increases, but then this goes here and is subtracted from here. So what happens is this decreases here. So that's what we mean by negative feedback. That if this increases here, the output then causes to counteract this particular change here. And in fact, it's not just here. If anything, let's say inside the op-amp, inside the amplifier also something increases, which may cause an increase in this particular voltage here, then it's fed back, and then the input goes down. So it tries to counteract that. It tries to create an effect which is opposite to whatever is causing increase here. And same thing will happen if, let's say, due to some reason the output voltage decreases. If for some reason the output voltage decreases, then this voltage will decrease. But then what is fed back will increase here, and therefore it will counteract that. So that's why we call it a negative feedback. In this case, note that if this goes up, and let's say the gain is negative, so this goes down, and then this goes down, and because this is being subtracted, so this goes up again. Right, so now it is being positive. If for some reason, let's say this quantity goes up, and then the output is being fed back to the input in such a way that it exaggerates the effect of that here. So that's called a positive feedback here. So op-amp circuits can be classified in open loop or open loop circuits or without feedback, or circuits which have feedback, and they are also called the closed loop circuits here. The closed loop circuits can be negative feedback or positive feedback. Now most of the circuits are negative feedback. They're often stable, and one can do a wide variety of things with feeding it in the negative direction. When you put positive feedback, the circuit tends to become unstable, and we often use such circuits for making oscillators, where you want the circuit to oscillate between two stable states. So most op-amp circuits will employ negative feedback, and that's where we will concentrate our attention here. So an example of a op-amp circuit with feedback, with negative feedback, is this inverting amplifier here that we had briefly mentioned earlier. So let's analyze this particular circuit. So our op-amp is here. Op-amp is Ri, A0LVI, and R0 here. Okay, and so we've connected an R1 now and R2 here. So this whole amplifier will now look like this here. And note that because we have connected to the inverting terminal here, so this is minus plus VI here. Okay. All right. So we can reverse the polarity. We can call plus minus VI here, but then we'll have to make this negative here to keep the circuit identical here. So it's up to us to call which terminal positive and which terminal negative. If I reverse it, then I have to reverse this one here. Reverse the definition of Vi, then minus AOL Vi. All right, so let's, this is the circuit that we'll get. Let's do a quick nodal analysis. Vs minus Vi, this is 0, so this is Vi by R1 will be equal to Vi by Ri plus Vi minus V0 by R2. So that's one that we get. And the other one is we can do a nodal at this particular point, so we can write this equation here. A0L is the open loop gain here. This particular equation can be rearranged. So this was a part of one of our exams, a circuit like this. So we can rearrange this particular equation. Vs by R1 is minus V0 plus this particular, these terms here. And we can rearrange this particular equation to get Vi in terms of V0. Now that's where we will make our assumption here. We'll assume that our op-amp is, let's say, has very high gain. So A0L, open loop gain, tends to infinity. And if open loop gain tends to infinity, if this term tends to infinity, the denominator tends to infinity, so therefore Vi will tend to 0. Vi will tend to 0. So in these circuits, in op-amp circuits with a negative feedback like this, if the gain is very, very large, then Vi tends to equal to 0 here. And so this is called the virtual ground property here. When Vi becomes equal to 0 here, or Vi is very close to 0 here, this node, the node that you see here, is like a ground terminal here. Because then if the voltage is 0, then the value of this particular node is 0 here. But it's a virtual ground. We'll see why we will call it a virtual ground here. So as A0L tends to infinity, Vi tends to 0 here. Now, if Vi tends to 0 here, note that there is a very high input resistance also. So that implies that the current goes to 0 here. Okay, so the current goes to 0 here. And so no current really flows in or out of either inverting or non-inverting terminals of an ideal op-amp. Okay, so that's because the input voltage Vi is 0. Vi tends to be 0 here. And therefore the current flowing through this particular resistor is 0 here. All right, so that's the other property of the op-amp that is there when you use it in the feedback mode that you see here. Okay, so that's an interesting thing here. If you look at this this node here, so it is what we are saying is that this value of this particular node is 0. So it's like ground, or this particular node, you may think that is shorted here, but it's not really shorted because you have connected a very high value of resistor here. So its value is equal to ground, but the current is also 0 here. So it's an element, it's appearing to be an element which is simultaneously a short and an open circuit here. So if somebody tells you V1 minus V2 is 0, we would think like this is like a short here. On the other hand, if somebody tells you, well, I is equal to 0, going through this particular one, you'll say I equal to 0, well, it's like an open circuit here. Okay, so can something be both a short as well as an open circuit? Well, our op-amp is between these two terminals is behaving like this here, between here and here. It is a short in the sense that this voltage is same as this voltage here, ground. And it's an open because there is no current going in here. Because the voltage across these two pair of terminals is very small and the resistance is very, very high. So the current is 0 here. So it's like an open circuit here. So all our op-amp circuits with negative feedback will have this particular property here. Vi equal to 0, like a ground. And but not exactly, that's why we call it like a virtual ground, not exactly like a ground. Because if we had this resistor R1 like this and it was actually ground, then all the current would go into the ground here. On the other hand, in our case, the current that comes in here, well, the current cannot go in here. We are saying there's a very high resistance and the drop across that particular resistance is 0 and the current is also 0 here. Okay, so a real ground would have all the current here would have flown into the ground here. Okay, so but in this case, the current that comes in here will actually go up because nothing can go into the op-amp here because of the very high resistance, and Vi equal to 0 here. So very little voltage here along with very high resistance, so the current is negligible. Hence the name virtual ground. All right, so the virtual ground property is this. So when we use op-amp under closed loop condition, what it would effectively mean is that V1 will be equal to V2. So we'll use that property. But only under negative feedback condition here, not under open loop condition here, okay? So this property will not hold under open loop or under positive feedback, or even if the op-amp is saturated. Because for this property V1 equal to V2 to hold, we require the gain of the amplifier to be very, very high here. And when the op-amp is saturated, then V0 is not responding to V1 and V0 is not responding to V2 either. So it's no longer then in that high gain region there. Okay. So as long as these conditions are satisfied, that is under closed loop condition with negative feedback and the op-amp is not saturated, then we can assume V1 is equal to V2. All right, so there are two important properties for analyzing ideal op-amp circuits under negative feedback. So that's important. V1 equal to V2, and the other one is I1, this current I1 and I2 both are 0 here. So at the input side, op-amp appears like a short and an open circuit simultaneously. The two terminals are like short, V1 equal to V2, but at the same time, no current is flowing. So with that, let's analyze this particular circuit. This analysis of circuits and design of circuits now becomes very simple here. So because this terminal is ground, so this will also be ground 0 here. So this current we can very quickly calculate. The current will be equal to Vs by R1. Now where will this current go? It cannot go into the op-amp because we are saying the current is 0. So it goes here, Is. And therefore, we can write a simple Ohm's law, 0 minus V0 divided by R2 is equal to Is equal to Vs by R1. And therefore, V0 by Vs is minus R2 by R1. And so that's why we call it an inverting amplifier, because the output voltage is equal to Vs, but with a phase shift of 180 degree with a minus sign and with a ratio of R2 by R1 here. So that's what we were saying. Anybody can build an amplifier by connecting two resistors across an op-amp of a suitable ratio here. Now that's an inverting amplifier. If you want a phase difference of 0, you can connect the input at this side here. And R1 and R2 are still there. Note that there's always a feedback path. So again, V1 equal to V2. This is V1 and this is V2. I1 equal to I2 equal to 0 here. So if this value is Vs at this node, then this value will be equal to Vs. The two are the same voltages here. So the current flowing here will be equal to Vs by R1. The same current will flow through this one here, equal to Is. And then we can write V0 minus Vs by R2 equal to Is, Ohm's law across R2. And thereby we get V0 by Vs is 1 plus R2 by R1 here. So we call this as a non-inverting amplifier. V0 is equal to Vs multiplied by this quantity 1 plus R2 by R1 here. Okay. And so let's look at these examples here. How do we analyze this? So this is an inverting amplifier. V0 by Vs is minus R2 by R1. So V0 is 100 millivolt. In this case, V0 by Vs is 1 plus R2 by R1. So we get V0 equal to 110 millivolt here. R2 by R1 is 10. So 10 plus 1, 11. 11 multiplied by 10 gives us 110 millivolt. What would happen in this case? Well, we have this current 1 milliamperes. Where will it? This is 0 here. So this node will be 0 here. Fine. This current 1 milliamperes, the only path for it, it cannot go into the op-amp. The path for it is here. So it will go into this. And what will happen to this? It will come here and then flow into the op-amp here. So output voltage 0 minus V0, do an Ohm's law across this by 10K is 1 milliampere. So V0 is minus 10. So this is what this circuit is called current to voltage converter. Any current that is given here, you will generate an output voltage here, which is proportional to the current here, but with a phase difference here. Well, if you want to add up two voltages, Vs1 and Vs2, so you can use this particular circuit to add up here. So let's see quickly. So all analysis is being done by assuming those two properties, that the voltage across is 0 and no current is going. So this will be 0. The current here will be Vs1 by R1. The current here will be Vs2 by R2. The two currents will add up and will flow here, Is1 plus Is2 here. And therefore, do an Ohm's law across RF, 0 minus V0 by RF here. and you get V0 equal to minus RF by R1 Vs1 plus RF by R2 Vs2 here. So it adds up. You can choose RF by R1 and RF by R2 to be the same by making R1 equal to R2 equal to same. So V0 will become minus RF by R Vs1 plus Vs2 here. And therefore it's adding up the two voltages. The output voltages equal to the sum of Vs1 plus Vs2 multiplied by a amplifying constant. If you're not interested in amplification, you can make RF equal to R, right? RF equal to R. So it will be simply Vs1 plus Vs2 plus there is a phase difference of 180 degree. And if it bothers you, we can get rid of that also. Now there's an alternative way of analyzing this particular circuit. These amplifiers are linear, so superposition theorem is valid. So we can first calculate V0 due to Vs1, then we put this node to remove this particular shorted, and we can calculate due to Vs2, then we remove Vs1. And so the first one is an inverting amplifier. Note that R2 will not bother, this node is 0, and so R2 gets shorted out. And so it's just like normal inverting amplifier. So that's why I've written minus RF by R1 Vs1. The second one is R1 gets shorted out, this is 0 here. So this will be equal to minus RF by R2 Vs2. So this will be equal to Vs2, not Vs1. All right, so suppose somebody says design a circuit that would generate the following output given 3 input voltages, Vs1, Vs2, Vs3. We want this one here. So we note that V0 is, this particular circuit was doing the following, minus RF by R1 Vs1 minus RF by R2 Vs2 here. And so it's easy to see that maybe we can add a third thing here, and then we'll get minus RF by R1 Vs1 minus RF by R2 Vs2 minus RF by R3 Vs3 here. So now whatever value you want, 10, 4, 5, you can get by arranging the values here. So choose a feedback resistor, a convenient value, let's say 10K. Then R1 is 1K, R2 is 2.5K, and R3 is 2K, and our design is complete. We could build an adder in this particular manner also, where we will get rid of that minus sign here. So here what we are doing is analyzing it by superposition theorem here. So these are the two voltages that we want to add up, Vs1 and Vs2. So so we remove Vs2 here, and we have this circuit here, and it's easy to analyze. Note that R2 will come in parallel with R3, and so it's a voltage divider, R1. No current flows into it, so it's a voltage divider, so you'll get this voltage here. And after that, this R4, RF is nothing but a non-inverting amplifier. So it's easy to write. V0 equal to Vs1. This is the voltage divider, R2 parallel R3 divided by R2 parallel R3 plus R1 here, voltage divider at this, multiplied by 1 plus RF by R4. So it's a non-inverting amplifier. Similarly, for Vs, that's for Vs1, and similarly for Vs2, one can write it like this here. Right, so we'll get this equation here. Except that this particular equation is a little bit messy equation, and sometimes we use the word high entropy expression, entropy in the sense of disorder. So it's a highly disordered expression. I mean, it's better than the expression that we will get by mesh and nodal, but it's still a disordered expression. And we can define a resistance as R1 parallel R2 parallel R3, and you can verify that you can write V0 now as Rp by R1 Vs1 plus Rp by R2 Vs2 multiplied 1 plus Rf by R4. So a much simpler expression with Rp defined as the parallel combination of R1, R2 and R3 here. Okay, and so it's a low entropy, it's a more orderly as compared to this particular expression here. So if you wanted to add up the two voltages Vs1 and Vs2, so you could take appropriate values of Rp by R1 and Rp by R2 here. If you choose Rp by R1 and Rp by R2 to be equal, it will get Vs1 plus Vs2, and the whole thing gets multiplied by some gain factor here. So if somebody asked design a circuit that would generate 10 Vs1 plus 4 Vs2, well, you could use a circuit like this here, and let's leave it as a homework problem here. Okay. So in the previous circuit, when we had this kind of an adder, there was a negative sign, And if negative sign bothers you, we could use this circuit here. But then we can also, what we can do is we can also add another stage here. So the output here is minus Vs1 plus Vs2, and we can add another stage here. So that one will add another -1 here. So V01 is minus Vs1 plus Vs2, and V0 equal to minus V01 here, because the ratio is equal to 1 here. And therefore, V0 equal to Vs1 plus Vs2 here. So it's a simple, the two stage together will add up the two voltages Vs1 plus Vs2 here. Okay, so the negative sign we can get rid of by adding another stage like this here. But we have made some assumption here. And the assumption that we have made is the following, that the two stages are not interacting with each other. Not interacting in the sense that this stage does not affect the output property of this particular stage here. So this relationship that we derived here, we derived it under the assumption that nothing was connected here. Now that we connect this particular circuit, this relationship, we are assuming that it still holds. Well, in general, that is not true. For op-amp circuit, it is true, but in general, for circuits, this is not true. And simple example will show you. So we have a voltage divider, and if we calculate V01, obviously V01 by Vs is 0.5. We have another voltage divider, V0 by Vx is 0.5 here, right? So and if we connect them together, then in a naive way, we would expect that V0 by Vs would be 0.5 multiplied by 0.5 here. Okay. We may assume that V01 equal to Vx. Since we are connecting it by a wire, so we would think that V01 will be equal to Vx, which is true. And we may assume that V0 by Vx equal to V0 by V01 is 0.5, and therefore the answer is 0.25. But we have made an assumption. When we actually connect the two, you know it very well, that actual value V0 by Vs is not 0.25, not 0.25 here, but is 0.2. And where is the error? The error is, yes, this is a voltage divider, V01 by Vs is 0.5. This is also correct, 0.5, no problem. But the moment you connect it, this part of the circuit comes in parallel to R here, and therefore modifies it. And so V01 is equal to Vx, no doubt, no error here. But then V0 by 1 Vs is no longer 0.5 here. So the moment you add this circuit to this one, the first circuit is affected here. And it's no longer a simple voltage divider. This part of the circuit also comes in parallel, as you can see here, to R. All right, so circuit 1 gets loaded by circuit 2. The circuit 2 acts as a load to the first circuit here. So circuit 1 gets loaded by circuit 2, and this output versus input characteristics gets modified here. So this loading effect, whenever we take two blocks of circuit and we connect them up, this loading effect we should always be aware of. And so this is what we mean. We have a circuit, and you understand the property of the circuit, V0 versus Vs here, and then you connect a load. And when you connect a load, V0 in general gets altered when we connect a load to it. So the relationship between V0 versus Vs gets altered by the load that is present here. But there's a certain condition under which every load will affect it, but there are certain conditions under which the change in V0 is very small. Example, 1K here, and 1 mega ohm here. Now, so the ratio was 0.5, the ratio was 0.5. Now you connect the two together, you will find V01 over Vs is still 0.5. The second one acts as a load. It loads the first one, but the loading effect is small because the resistances here are 1K and the resistances here are 1 mega ohm. We can describe this effect in terms of output resistance. So this circuit that we see here is output resistance looking from here between this terminal and ground, let's say. The output resistance will be, so whenever you want to calculate the output resistance of a piece of a circuit, you short the independent source. So this 1K and 1K will come in parallel. Output resistance is 0.5K. And the load is, when we look at it from this side, the load is 1 mega ohm plus 1 mega ohm, 2 mega ohm. So R0 is much smaller than the load resistance. So whenever the output resistance is much smaller than the load resistance, then the loading effect is minimal. And so if you're connecting two pieces of circuit and you want the second circuit not to affect the first circuit, then you have to ensure that the output resistance of this first circuit is much smaller than the load resistance. R0 is much smaller than RL, which is true in all our op-amp circuits here. So when we write this relationship, V0 is minus Vs1 plus Vs2, and then when we connect this particular one, we are still saying V01 is equal to minus Vs1 plus Vs2 here at this point, even after connection. The reason being is that there is no loading effect. The op-amps are designed in such a way that the output resistance of the op-amp, this particular circuit, is very, very low. So whether you leave this terminal open circuit or you connect something to it, the output is not getting affected here. So we'll assume that you can freely connect different blocks of op-amp circuits, and one block will not affect the characteristics of the second block here. Okay. All right, so let's look at this particular example. What would happen in this case? So note that we can calculate what is the output voltage here. So we have two inputs, so output voltage is minus 3 here. Right, so you can use superposition. So each one is like an inverting amplifier. This one is also like an inverting amplifier. So this is minus 3 here. This acts as an input to a non-inverting amplifier here. So we can use a non-inverting amplifier as a relationship, 1 plus R2 by R. So output is minus 9 here. Well, we've been talking about adders. We can build subtractors also. So now note that Vs1 we apply from here, and Vs2 we apply from on this side here. And we can analyze very quickly. This is a voltage divider, R3 by R2 plus R3. So whatever is the voltage here, the same voltage will appear here. So this is the current here. Now we can calculate the current. The same current would flow here. And apply Ohm's law across this. And rearrange it so you get an expression like this here. And let's simplify it here. So we get this expression here. So now let's choose R3 by R2 equal to RF by R1. R3 by R2 equal to RF by R1. If we choose it like this, it's easy to show that you can rearrange V0 equal to RF by R1, Vs2 minus Vs1 here. So we can subtract the two voltages here, Vs2 minus Vs1. So there are lots of interesting things we can do now with this op-amp circuit by using it by applying voltages to the inverting terminal or non-inverting terminal. We can add signals, we can subtract signals. By the way, we can also do a alternative analysis using superposition. So you calculate first due to Vs1 by removing Vs2. Then you calculate due to Vs2. And here you use the fact that this is like an inverting amplifier. Note that R2 parallel R3, no current flows here, so effectively this node is ground. Now in this case, this acts as a non-inverting amplifier. Inverting amplifier here, so you use this relationship. Non-inverting amplifier, so you use the relationship for non-inverting amplifier by calculating first the voltage here. And so analysis is made simpler by reusing results derived earlier here. So there's no need, if you can break the circuit into elements whose results you're already familiar with, so you use that to very quickly analyze and get the results that you want here. All right, so in these cases, it looks complicated, but conceptually fairly simple. We have several voltages, Vs1, Vs2, Vs3, Vs4 here. So use the superposition theorem to write down each value here. So due to Vs1, so remove all of them. Vs3, Vs4 are all shorted, Vs2 is shorted. You should be able to see that the only thing that matters is R1 and RF here. Inverting, minus RF by R2, Vs2 here. This one is R5 parallel R4 divided by here R3. Multiplied by 1 plus RF by R1 parallel R2. Note that when you're looking at Vs3 here, Vs1 is short, Vs2 is short, so R1 comes in parallel with R2. And the whole thing looks like a non-inverting amplifier. Okay. And we said that you can make things easier if you define R3 parallel R4 parallel R5 as a parallel resistor Rp. And then the whole thing you can write, you can verify that you can write it as Vs3 Rp by R3, Vs4 Rp by R4, and this one is 1 plus RF R1 parallel R2. Okay, so verify. So let's take this as an example. Suppose somebody wants V0 equal to minus 10 VS1, minus 4 VS2, 5 VS3 plus 2 VS4. So we have some two minuses here, so that's why we have two voltages applied here, and 2 plus here, VS3 and VS4, so two of them we applied here. So it's an example of adder subtractor, we call it. Some voltages are being added, some are being subtracted here. And we define RP is R3 parallel R4 parallel R5. So V0 is given by this expression here now. And so we can decide by choosing, let's say, RF equal to 10K. And then R1 is straightforward, minus RF by R1, so is minus 10, so it's fine. R2 also we can determine to get minus 4 here. When we come here, once we chosen RF and R1 parallel R2, so we get RP by R3 is 0.33. And we get RP by R4 is 0.133. And therefore, from these two, we can get R4 by R3 is 2.5. We can choose R3, convenient value, let's say 1K. So that gives us R4 equal to 2.5K. Then that gives us RP equal to 0.33K here. And then that gives us R5 of 0.625K. Okay, so let's stop here.